Okay, we're going to review composition of functions. Composition is when you take the function of a function. You actually have a function as an input rather than a number or a variable as an input. So my two given functions are f of x equals the natural log of x plus 1 and g of x equals the sine of 2x, and I want to find f of g of x. Please be aware that this could also be written in this form, that little circle in there. Textbooks will do it both ways. What that means is we're going to start with the innermost function. We're going to start with this g of x function. And we're going to replace g of x with whatever my g of x function is. So this now says f of whatever g of x is, which is the sine of 2x. Now I'm going to take this sine of 2x and place it into my f function. The natural log of the sine of 2x quantity plus 1. Now please note that when you write g of f of x and f of g of x, that they are not always going to give you the same answer. So let's do this in reverse. Let's start with f of x as my input. So I want g of the natural log of x plus 1. I then want to put all of that in where I have x in my g function. So the sine of 2 times the natural log of x plus 1. Notice those do not look anything like each other. They are not commutative operations. There's a special case when you'll get the same answer, and that special case is what we're going to talk about next when we talk about inverses of functions. Inverses of functions. A function has an inverse when it is a reflection over the line y equals x. Literally every x and y are replacing each other so that every x value becomes a y, every y value becomes an x. When you have two functions that are inverses of each other, the composition in both directions, f of g of x and g of f of x, will always result in x. So let's try a simple example and then a more complicated example. Okay, here are two examples. One is a little bit easier than the other one. We're going to try them both. If you're given the function f of x equals the quantity x plus 2 divided by 3, find the inverse and then prove that it really is the inverse by using compositions. All right, so we're going to start with our function is f of x equals x plus 2 divided by 3. Well, f of x really is y, so this really says y equals the quantity x plus 2 divided by 3. So the first thing I'm going to do is I'm going to exchange the x's and the y's, and I'm going to have x equals the quantity y plus 2 divided by 3. Undoing operations, I multiply both sides by 3 and subtract 2 to get this as my inverse function, or g of x, or whatever you want to call it. And now I want to prove that if f of x is quantity x plus 2 divided by 3, and g of x, its inverse, is 3x minus 2, I want to prove that those really are inverses by using compositions. So I'm going to prove that f of g of x and g of f of x will come out to the same answer. So f of g of x gives me f of 3x minus 2. I put that g of x in. Now I'm going to take this expression and put it in wherever x is in my original function. So I'm going to get 3x minus 2 plus 2, that whole thing divided by 3. Well, those parentheses are meaningless, so I really have 3x plus 2 minus 2. The plus 2 and minus 2 are going to go away, so I'm going to have 3x divided by 3, which ends up giving me x. I'm going to try it in the other direction, g of f of x. So this time I'm going to start with the g function and put my f function, x plus 2 divided by 3, wherever I have x in my g. So 3 times x plus 2 divided by 3 minus 2. Well, those 3's I can factor out, and I'm left with x plus 2 minus 2, which turns into just x. And so these are correctly inverses of each other because composition in both directions worked. The next example is somewhat more difficult, so we're going to turn to the next page so we have a little more space to work with. And I'm going to write my equation. Instead of f of x equals e to the x plus 1, I'm going to write y equals e to the x plus 1. Okay, so we have the function y equals e to the x plus 1, and I'm going to find the inverse, and I'm going to find the inverse by replacing the x with the y and the y with the x, so I have x equals e to the y plus 1, and then I'm going to change from an exponential equation to a logarithmic equation. One of the ways I'm going to do that is by taking the natural log of both sides. So the natural log of x is equal to the quantity y plus 1 times the natural log of e. We all know that the natural log of e, it really is just 1. So this says the natural log of x is equal to y plus 1. The natural log of x minus 1 is equal to y, and that's my inverse function. So now we're going to call that g of x. G of x is the natural log of x minus 1. F of x is my original function, which was e to the x plus 1. And I want to find out if these are truly inverses, if the composition of f of g of x and g of f of x both come out in the same x answer. So I'm going to do f of g of x first. So my g of x function was the natural log of x minus 1, and I'm going to put that in wherever x is in my original function. So I have e to the natural log of x minus 1 plus 1. So I have e to the natural log of x, which of course is just x. I'm going to do it in the other direction, g of f of x. So I'm going to go to my f of x function, which was e to the x plus 1, and I'm going to put that in my g function. So the natural log of e to the x plus 1 minus 1 is simply x plus 1 minus 1, which is x, and so these are indeed inverses of each other.